Alright, this is 7-2, triangles and angles. So this whole unit is going to be about triangles. We love triangles. In fact, I think the next 2 units. So we're going to just sort of get an introduction to triangles and the angles that are inside of them, and also side lengths a little bit, and their relationships. So fun stuff. So this first idea here is it's asking us, can we make a triangle out of any 3 side lengths? So it says explore, use a ruler to draw triangles with the given side lengths, and I encourage you to try to do this. Actually, pause me and do this. So if you've done that, you realize that 10 centimeters, 5 centimeters, and 7 centimeters makes a triangle, and this is like sort of rough estimate because I am not measuring 10 centimeters and 5 centimeters and 7 centimeters makes a triangle. But something rough happens when we get to 1 inch, and 3 inches, right? So 3 inches is pretty long, and then 1 inch and 1 inch don't get very far, right? Like we cannot make those into a triangle. No matter what we try, it always ends up being disjoint, meaning that you can't have all 3 of the sides meet. And that's because these 2 sides are too short, right? We run out of space. Together they only equal like 2 inches, which is not as long as this third side at 3 inches. So the idea here is that you can't make a triangle out of any 3 side lengths. In particular, in order to make sure this doesn't happen, any 2 of the side lengths have to be more than the sum of, let me say that again. Any side length has to be more than the sum of the other, less than the sum of the other 2. I have to say that 3 times to make sure it's right. Let's write it down here and we'll make more sense out of it. It says, in order to be able to form a triangle, no single side can be equal to or longer than the sum of the other 2. Longer than the sum of the other 2. I will write that word out. So in this one, the problem is that the side that's 3 inches is longer than the sum of 1 inch plus 1 inch, right? So that is what makes it not work here. It can't be equal to or longer than the sum of the other 2. So let's just the idea here is that it can't be equal to either. So what would happen if instead of 1 inch and 1 inch we had 1.5 inches and 1.5 inches? The problem with that is that if you can make them touch, you can make these 2 touch, but you have to make them flat. Essentially, you end up with a triangle that looks like this, which is not really a triangle, we've decided. In math, that's not a triangle. So it can't be equal to or longer than the other 2. So here's an idea that we're probably familiar with. We've been actually using it, especially in our circle unit. We've already used this. The interior angles of a triangle always add to 180 degrees. This has been proven. We use this information a lot. So we'll just use that really quickly to find the missing angles for these triangles. Number 1 has 2 angles, 87 degrees and 36 degrees, and then this third angle, we don't know, has to equal 180 degrees. So we do some subtraction and we find out that this angle has to be 57 degrees in order for that triangle to work. This one has a 90-degree symbol, meaning that one of the angles is 90, the other one is 34, and then something equals 180 degrees, and we do some subtraction and find out that that one has to be 56 degrees to make this work, this last angle over there. And last we have this triangle here, and this one's a little bit interesting, right? We only have 1 angle. I know this is kind of far, but this 22 degrees goes in there. And then we just have like these 2 symbols down here for the angles, and what this means, this line through those angles, it means that they're the same. So this is going to look a little bit more algebra-y than the other ones do. And that's because we do have to do a little bit of algebra here. We only have 22 as one of the angles, and then we don't know the other two, but we do know that they're the same. So I'm going to call it x, because we are wondering what those angles are, equals 180 degrees. So we just named this value x, and because they're the same, we're just calling them both x. So x plus x, that's two x's, like that. And when we see that, this looks very much like an algebra problem that we can solve, right? We take away 22, we take away 22. That gives us 58 on this side, equals just 2x. And then we'll have to divide by 2 because we have 58 degrees left for both of those angles. And in half, that makes... whoa, okay. So let me fix that really quickly. I'm sure you probably noticed this. I took away 22 from 180 and got 158. That's better. So the two angles on the bottom of the triangle have to be 79 degrees because that's half of 158. So both angles down there are 79 degrees. And if you could figure out that that was 79 degrees without doing this much algebra, then more power to you. I support you. Usually people can figure it out without that algebra, but I like to show the algebra just as a way to get you ready for other kind of stuff that's similar. So let's talk about some vocabulary with triangles here. Everyone please appreciate the faces that are on these triangles. They're very important. So we're going to classify triangles using interior angles. So we sort of have a system for naming triangles based on their interior angles. For this one, acute triangles, which is a very cute name, right? Acute triangles, all the angles are less than 90 degrees. None of the angles can be bigger or bigger than or equal to 90 degrees, which is very much possible. Those are acute triangles. Right triangles have one angle equal to 90 degrees, this one. Hopefully you're familiar with right angles. Right angles come up a lot. And we'll get real familiar with right angles later. And then obtuse angles have one angle that's bigger than 90 degrees. Just one angle. You can't have all of the angles bigger than 90. It's impossible. But you can have one angle bigger than 90. The other angles end up being kind of small, but that makes that an obtuse triangle. All of these words are words that we use in normal English, which is why the faces are like this. Obtuse people are like just kind of angry all the time. Anyway, it's fun stuff. Equilateral triangles. Equilateral triangles are lovely, like perfect triangles. All of their angles are the same, and also all of their sides are the same. All equal angles and all equal sides. We love equilateral triangles, they're lovely. Isosceles triangles are triangles where two of the angles are the same, and so are two of the sides. The third angle and the third side are not equal. So two equal sides and two equal angles. And specifically it's those two sides. Whenever these are equal, then the sides that are attached above are also equal. So you can't like change this to say like, oh, this side is equal, because that one doesn't work. So it's specifically that relationship. So make sure to note that on your book. Scalene triangles have no equal sides or angles. So all of its angles are different and all of its sides are also different. So they're like the ugly cousin. None of the angles are equal. Or sides. So you might notice that it always has the same amount of equal sides and equal angles. And that's actually true all the time because of a specific relationship that happens within a triangle with its angles and its sides. So this is an activity that I encourage you to pause me and do, where you measure each triangle the side lengths and the angles and figure out which is the biggest and which is the smallest. So for the purposes of this today, I'm just gonna indicate the largest angle and the longest side because it's something that I can see. I don't have to measure. This one's the largest. Oh, I'm also highlighting it in the wrong color. It says the longest side in yellow, so I will do that. Largest angle, largest angle, largest angle. And then the longest side is this side. And this side. And this side. So I want you to notice here that the largest angle is always exactly opposite the longest side. So it has this sort of relationship in all of them where the angle is opposite the longest side. And that's in fact always true. And if you do this with the smallest angle, you'll find that the smallest side and the smallest angle also have the same relationship, where the smallest side is always opposite the smallest angle. And that's always true. The angles inside of a triangle have a really specific relationship with the side lengths, and it has to do with opposites. And the way that I visualize what opposites in triangles mean is with like a flashlight idea. So if the angle is a flashlight, the side that it's shining on is its opposite. So we're sort of visualizing, and I will erase this. Actually, I'll just use this. We're visualizing a triangle like this, right? And here's the angle. It's the flashlight, and the side that it's shining on is its opposite side. And that's really important to know. Opposites are where this relationship happens, where the longest side and the largest angle are always opposite each other. Largest angle is opposite longest side. And same thing for the smallest angle. Is opposite the shortest side. And so this is that opposite relationship where the angle is sort of shining as a flashlight onto its opposite side. So this little activity is just placing these angles and the sides in the correct places. So I can tell that this angle is the biggest, so I'm going to put the biggest angle here, 88 degrees. The smallest angle is 34 degrees, and then the middle one is 58, so I just put those in the right place. I know that the longest side has to be opposite the largest angle, so this one has to be 34. And then this smallest side has to be opposite the smallest angle, so this is 14. And this last one is 24. Okay, so we have a proof to do, and then some practice problems here. And this is called the exterior angle theorem. So the exterior angle of a triangle just means that if you extend one side of the triangle, so like I have this triangle and I've extended this side length beyond the triangle, it creates this angle outside of the triangle called an exterior angle. So we're going to prove some interesting information about that exterior angle here. So we're going to just start with the ideas of the idea that inside of a triangle always adds to be 180 degrees, and also the idea that supplementary angles also add to be 180 degrees. Okay, so our given information, angle E is the exterior angle to the triangle ABC, meaning it was created by extending one of the sides of the triangle past the vertex. Vertex meaning the corner. What does that mean? Angle E and T together form a straight line, which means they are supplementary. Supplementary. To write small for that. That means that angle E and angle T added together have to be 180 degrees. We know that. Then since the interior angles of the triangle add to be 180 degrees, that means that angle S plus angle R plus angle T, those are the inside angles of the triangle, also add to be 180 degrees. Since both are equal to 180 degrees, so we're talking about this mathematical sentence and this mathematical sentence are both equal to 180 degrees. So that means that they are the same, right? Angle E plus angle T is the same as angle S plus R plus T. So I'm just going to write that down here. Angle E plus angle T equals angle S plus angle R plus angle T. They're equal because they're both equal to 180 degrees. And I want to bring your attention here to the fact that we have angle T on both sides. So we're allowed to do the same thing on both sides of the equation. So what if we took away angle T on both sides? That would cancel that and also cancel that, which means that what we have left is angle E is equal to angle S plus angle R. So let's look at what that actually means in the triangle. Angle E is this outside angle, and angle R and S are the opposite interior angles. So what we just proved is that this angle outside here is equal to this angle plus this angle. So you add those two angles together and they're equal to that exterior angle. So our conclusion is that the exterior angle E, and this is going to be like a long sentence, that's why we have a long line, is equal to the sum of the other two interior angles. Perfect. Okay. So let's do some problems. So it just means that this outside angle and the two other interior angles are the same. Okay, and so we're going to summarize really quickly that this exterior angle out here, we'll call it A, and B and C. So angle A equals angle B plus angle C. This is just, we just proved this, but it's kind of hard to see the theorem from the proof, so I'm just double checking that we have this information here. If we add B and C, we get A. That's the idea here. So we're going to just practice this really quickly. This is an exterior angle. This is like the outside, and this is A and B in here. So we know that if we add those two angles, which is 21 and 36, it will equal the outside angle. So that makes 57 degrees. So this is 57 degrees out there. This one gives us the outside angle, but not this one on the inside. So we have a missing angle there, and then these two. So I'm going to name it X just for the sake of being algebraically sound there. So we have 144 equals 74 plus whatever X is. So algebraically we can take away 74 from both sides and we get 70. I think. Yeah. 70 degrees equals X. So X is 70 degrees. Fantastic. Yeah, so we'll call it good there. So that was our practice problems. Remember these, we didn't do any practice of these classifying angles, but those are important to remember.